Hi, and welcome back to the wonderful world of the scientific hypothesis. My name is Brad Alger. Sometimes in a scientific paper, you'll read that a particular condition is a sufficient explanation for some phenomenon, and someone else will object that it's necessary but not sufficient. Or you'll hear that the gold standard of a necessary and sufficient explanation for some observation has been identified. While many scientists are familiar with the terms necessary and sufficient and use them appropriately, not everybody does. If you think you might be in the latter group, or if you just want a bit of review, this video is for you. We'll straighten things out with a few basic examples. Even though the ideas themselves are quite straightforward, it's easy to get mixed up. Most importantly, we'll show how the ideas relate to the broader issues of the scientific hypothesis and scientific thinking that we're focused on. So we'll cover what we need to know about necessary and/or sufficient conditions. We'll start with a definition of what the terms mean and show how they're related to each other. And then, most importantly, we'll see how they're related to the scientific hypothesis. So just a quick overview. In a necessary relationship, one statement must be true in order for another to be true. In a sufficient relationship, if one statement is already known to be true, then we can infer that another statement must also be true. And finally, in the gold standard, necessary and sufficient relationship, each statement implies the other. Either both are true or both are false. And we'll see some examples. Here's an example of a necessary but not sufficient relationship. We'll start with the idea that life on Earth requires water. What can we conclude from this? The statement implies that water is necessary for life. Without water, there is no life. The statement does not, however, mean that water is sufficient for life. Life also requires air and nutrients and so on. Notice, however, that the statement does imply that the presence of life is sufficient to conclude that water is available. Since water is necessary for life, if life exists, we can be sure that it has access to water. To put this thinking in a general context, let's consider the case of scientific hypotheses and predictions. True scientific predictions are necessary but not sufficient to prove scientific hypotheses are true. A true hypothesis makes true predictions. A prediction must be true if the hypothesis is true. A true prediction does not, however, guarantee that a hypothesis is true. So a true prediction is a necessary but not sufficient condition for the hypothesis to be true. Let's look at our familiar case of the pathetic fish in the pond that are dying, and we hypothesize this is from a lack of oxygen. The prediction then is that the oxygen level in the water will be low, and we'll test this by measuring the oxygen directly. If the oxygen level is adequate, the hypothesis is false. Since a true prediction is necessary, a false prediction means the hypothesis is false. If the O2 level is low, then the hypothesis might or might not be true. The data are consistent with it. However, other factors, for example, chemical runoff from nearby farms, could have killed the fish, so a true prediction does not mean the hypothesis is true. The truth of the prediction is not sufficient evidence, in other words, to prove the truth of the hypothesis. So here's an example of a different kind of relationship. Given that animals require oxygen and there are fish in the pond, what follows? Well, there must be oxygen in the pond. Since oxygen is necessary for animal life and since fish are animals, the presence of fish implies there is oxygen in the water. Now, in fact, the presence of fish is sufficient evidence to conclude there is oxygen in the water. Now consider, is the presence of fish necessary to conclude there's oxygen in the water? And clearly not. There could be plenty of oxygen, but no fish because they've all been caught or killed by toxic bacteria. So the presence of fish is sufficient, but not necessary to determine if there is oxygen in the water. We could, for example, measure the oxygen levels directly with instruments. So finally, we come to the all-important gold standard of necessary and sufficient conditions. In the wild, All baby bears are born to mother bears. So if you see a baby bear, this implies there must be a mother bear. And to be a mother, a bear must have given birth to a baby bear. So a mother bear implies there's a baby bear. We conclude that a baby bear is necessary evidence of a mother bear, but also that a baby bear is sufficient evidence for a mother bear. A baby bear is necessary and sufficient evidence of a mother bear. Each one implies the other, and likewise then, a mother bear is necessary and sufficient evidence of a baby bear. We can also state the relationship in a negative sense, and we'll see why this is important in a minute. If there is no mother bear, there cannot be a baby bear, and if there is no baby bear, there cannot be a mother bear. The absence of one implies the absence of the other one. So a necessary and sufficient relationship is airtight. Either both parts are true or both are false. Now you might think it would be easy to adapt necessary and sufficient reasoning to science. However, notice that we haven't learned anything new about bears or biology. The example just restated what we already understood from the words mother and baby. In fact, these necessary and sufficient relationships are matters for philosophy, not science. The question remains, can scientific evidence attain the level of logical certainty required for necessary and sufficient relationships? Now, we know that predictions derived from hypotheses are necessary. The question is, can tests or predictions produce sufficient evidence that a hypothesis is true? Let's start by looking at a simple biochemical reaction, the activation of an enzyme called CAMK2 by the element calcium. Now, normally in cells, calcium is limiting, and so calcium binds onto a small molecule called calmodulin, or CAM. This then activates CAMK2. Normally increased calcium binds CAM and then activates CAMK2, and therefore activation of CAMK2 only happens if calcium increases. At first, calcium looks necessary and sufficient for activation of CAMK2. But to see the problem, try stating the relationship negatively. If CAMK2 is not activated, can we conclude that calcium is not present? No. CAMK2 activation might be, for example, blocked by an antagonist of the little molecule calmodulin, even in the presence of calcium. Calcium is only one factor that affects CAMK2, and so calcium is necessary but not sufficient to activate CAMK2. And in general, in empirical science, we do not know all of the factors that could affect the relationships among the things that we're studying. Ultimately, the discovery of genuine necessary and sufficient conditions is, like the attainment of 100% certain truth, an ideal but unachievable goal for empirical science. Now let's just run through some conclusions that we've touched on here. A necessary condition must be present for another condition or an event or phenomenon to occur. A sufficient condition guarantees that another condition, event, or phenomenon had to occur as well. In science, predictions are necessary but not sufficient to prove the truth of a hypothesis. Sufficient but not necessary conditions can provide relevant evidence without always rigorously testing hypotheses. Necessary and sufficient conditions occur mainly in philosophical contexts regarding logical statements. Necessary and sufficient conditions rarely occur in empirical science because inevitable unknown factors rule out definite conclusions. Thanks for watching. Remember to give it a thumbs up if you like it and subscribe to hear more. See you next time.